Hello, this is Richard Hammack's Calculus 1 course. We are in part 4 of the course on applications of differentiation. Today in lecture 35, we'll talk about an interesting result called the mean value theorem. But before beginning, let me pause and say a few words about the structure of part 4 of the course on applications of differentiation, where we've been and where we're going. We started out in lectures 30 through 34 on the theme of maxima and minima, culminating with optimization problems. Today we'll take a slight change in direction and talk about the mean value theorem, which follows from max and min, and it has several important consequences, especially for part 5 of the course. Then in lecture 36, we'll talk about what are called differentials and approximations. They're useful later in calculus. In 37, the topic is Newton's method. It's a way of using derivatives to solve equations. And then, in lectures 38, parts A and B, we'll talk about what's called L'Hopital's rule, and it's a means of using derivatives to evaluate limits. So the theme here, as you can see, is applying derivatives to other problems. Today, in lecture 35 on the mean value theorem, we'll break it up into 3 parts. We'll first of all talk about what's called Rolle's theorem, which is not particularly useful. It's a technical result. Its importance is that it leads to the more important topic of the mean value theorem. And then we'll look at some consequences. So let's jump right in with Rolle's theorem. Rolle's theorem applies to the situation that's illustrated here. There's a function f of x defined on a closed interval from a to b. And it so happens that f of a equals f of b. The function starts out at height f of a, the height changes, and by the time you get to b, you're at f of b, which equals f of a. You'll notice there's a high point on the graph right here, which happens at an x value of c. And the slope of the tangent line at c, which is f prime of c, equals 0. What Rolle's theorem says is that you're always guaranteed, under this setting, to have such a point c. In words, Rolle's theorem says, suppose f of x is continuous on a closed interval from a to b, as it is here, and differentiable on the open interval from a to b, meaning that for any point x between a and b, the derivative exists, and also that f of a equals f of b, as it does here. Rolle's theorem asserts that under these conditions, that there is a number c in the open interval from a to b for which f prime of c equals 0, as shown here. This is totally believable. Your intuition tells you this has to be true, but Rolle's theorem pins it down. And you can see why Rolle's theorem is true. You've got a continuous function on a closed interval, so you know it has an absolute maximum or a minimum occurring at some point c. And so at c, either the derivative is 0 or it's undefined. But this function is differentiable on the open interval from a to b, so the derivative there can't be undefined. It has to be equal to 0. So Rolle's theorem follows immediately from what we've done in the first part of part 4 of the course on max and min. And by itself, this is not a very useful theorem. You'll never use it. Its importance is that it leads quickly to the important topic of today, the mean value theorem. And let's go to that. The mean value theorem applies to the situation that's illustrated here. Kind of like Rolle's theorem, except f of a is not necessarily equal to f of b. You have a function defined on a closed interval from a to b. starts out at height f of a, and then it changes, it varies, and at x equals b, you're at a height f of b, which may be different from f of a. Now in this picture, imagine connecting a straight line between the point a f of a and b f of b, as indicated here. And this straight line is going to be significant in the statement of the mean value theorem. In particular, take note of its slope. Its slope m would be rise over run, and the rise is f of b minus f of a, and the run is b minus a. So this connecting segment there has slope f of b minus f of a over b minus a. Now think about picking a number c between a and b. There's a tangent line at x equals c, and as we know, its slope is m equals f prime of c. And imagine varying c, and that changes the tangent line. As c marches down towards b, the slope of that tangent line changes. It has all kinds of different slopes. But there is one value of c, it looks like right here, where the slope of that tangent line, m equals f prime of c, is the same as the slope of this connecting line. F prime of c, the slope of the red line, equals f of b minus f of a over b minus a. The mean value theorem asserts that you can always find such a number c under this circumstance. In words, the mean value theorem is this. If f of x is continuous on a closed interval from a to b, as it is here, and differentiable on the open interval from a to b, then, the theorem asserts, there is a number c in the interval from a to b for which f prime of c equals f of b minus f of a over b minus a. That's, in this picture, this number c right here, where the slope of the tangent line equals the slope of the connecting line. The mean value theorem says that under this hypothesis, you can always find such a number c. I'm not going to prove the mean value theorem here. You can read about it in the text. It's a pretty simple proof, and it follows pretty much immediately from Rolle's theorem. I want to point out in the mean value theorem that this number c is guaranteed, but what it's saying is that there always is such a number c. There could be more than one number c that meets this condition, f prime of c equals f of b minus f of a over b minus a. For example, the picture might look like this. Here's your function, f of x, defined on the interval from a to b. Here's the connecting line between the two endpoints. Its slope is f of b minus f of a over b minus a. And notice you've got one c here, where f prime of c equals the slope of the connecting line. It looks like there's another number c right here, where the slope of that tangent line is the slope of the connected line. And there's a third number c right here, where this slope equals the slope of the connecting line. So the mean value theorem says that under the condition where f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there is at least one number c in the open interval for which this equation holds, and possibly more, but at least one. It's guaranteed, and that's what the mean value theorem says. Here's an example that gives a way of thinking about the mean value theorem, a kind of thought experiment. And I believe that after seeing this example, you'll realize that you have long had an intuitive understanding of the mean value theorem even before you knew any calculus. And the thought experiment is this. Suppose you drive 30 miles in 20 minutes, which is a third of an hour, on a straight stretch of road, 30 miles long. Let's say you start out at time t equals 0 on the left, and you start driving, and then at time t equals 1/3 of an hour, you've just completed your trip. So the question I want to pose here is, did you ever break the speed limit? And let's say the speed limit is 75 miles an hour. Well, your intuition says, yes, you did. And the reason is that your average velocity for the trip was distance traveled over time elapsed, which is 30 miles over a third of an hour, which works out to 90 miles an hour. So you must have been speeding at some point on the trip if your average velocity was 90 miles an hour. It's intuitively obvious, but actually this intuitively obvious fact is the mean value theorem. Look at it this way. The mean value theorem confirms this in the following way. Let's say your position at time t is f of t. That's your distance from your starting point at time t. And we know under this circumstance that your velocity at time t is given by the derivative f prime of t. Think about what the mean value theorem says about this function f of t on the interval from t equals 0 to t equals 1/3. It says this: at some time c, your velocity was f prime of c, which is f of b minus f of a over b minus a, where a is 0 and b is 1/3. That's the mean value theorem. And f of 1/3 is your position at time t equals 1/3, that's 30. And f of 0 is your position at time 0, that's 0. So this quotient is 30 minus 0 over a third minus 0, which is 90 miles per hour. So the mean value theorem guarantees at least one time c, where your exact velocity is f of b minus f of a over b minus a, which is 90 miles per hour. That's the mean value theorem. You can look at your f prime of c as being your exact velocity at time t equals c, where this right-hand side is your average or mean velocity of the trip. So what this is saying is, you can phrase the mean value theorem this way. The average rate of change of f of x on the closed interval from a to b equals the exact rate of change of f of x for some value x equals c. The mean value theorem asserts that your average rate of change equals your exact rate of change at some point. Let's move on to some consequences of the mean value theorem. First of all, there's a theorem that asserts that if f is differentiable on an open interval from a to b and f prime of x equals 0 for all x in the interval from a to b, then f has to be a constant function of the form f of x equals c. This theorem should be pretty intuitively obvious to you. It's saying that if the derivative of a function is 0, then that function has to be a constant, which you probably believed anyway. It really comes into focus when you look at a picture of this situation. Imagine a function y equals f of x defined on the interval from a to b with the property that no matter how you pick x between a and b, the derivative is 0. And that means that the slope of a tangent to this graph is equal to 0 no matter where you are. And it seems clear that that graph could never rise nor fall, so it would have to be a horizontal line at height, say, some number c, meaning that f of x equals c. It seems intuitively clear, but nonetheless we can pin this down and prove it using the mean value theorem. And the proof would run this way. Let's take any x in this interval from a to b. So take any x, say right here, and what we want to do is show that there's a number c such that f of x equals c, no matter how we pick that number x. And what we're going to do to prove this is apply the mean value theorem not to the interval from a to b, but rather to the interval from x to b. By the mean value theorem, there is a number c in this interval from x to b, for which f prime of c equals f of b minus f of x over b minus x. The difference in the f values between b and x divided by b minus x. In the hypothesis of this theorem, it stated that f prime of x equals 0 for all x. So in particular, for this number c, which let's say maybe it's right here, we would have to have f prime of c equals 0. So this equation becomes 0 equals f of b minus f of x over b minus x, and cross-multiplying 0 times b minus x equals f of b minus f of x, or 0 equals f of b minus f of x, and then we get f of x equals f of b. But notice here, the f of b is a constant. We've just shown that no matter how we pick this x, f of x has to equal the number f of b. Well, just call this number f of b c. It's a constant after all. And we conclude that f of x equals c no matter what x is. And therefore, f of x has to be the constant function f of x equals c. So this should be a pretty intuitively clear statement or theorem, as I said. But notice how the mean value theorem really dots every I and crosses every T and proves it conclusively. Here's another theorem that's going to be especially useful to us, especially in part 5 of this course. Suppose we have two functions f and g that are differentiable on an interval from a to b. And I've illustrated that here. Here's the function f, and there's the function g. That's just the setup. Here's what the theorem says. And I'll give this to you in two parts with an incomplete sentence first. If f prime of x equals g prime of x for all x in this interval, then something significant is going to happen. And I want to jump down to this picture to convince you what that significant thing is going to be. We have here in the setup that we're assuming that f prime of x equals g prime of x for all x. So if you take an x, say right here, f prime of x equals g prime of x, meaning the slope here is the same on f is the same as the slope on g. Moving to another x, the slope on f is the same as the slope on g. The slope on f is the same as the slope on g. The slope on f is the same as the slope on g. F prime of x equals g prime of x for all x. That's what's illustrated here. And looking at this, you start to see a relationship between the graphs of y equals f of x and y equals g of x under the assumption that their derivatives are equal. It looks like they have the same shape, that f of x is just g of x moved up some number of units. Say c units. You would surmise from this setup, just looking at this intuitively, that f of x has to be equal to g of x plus c for some constant. That's what this theorem says. If you've got two differentiable functions on an interval and their derivatives are equal on that interval, then one function is just equal to the other function plus a constant c. And we can prove this as follows. Imagine we've got this set up as stated here where the derivatives are equal for all x in the interval. And we want to conclude that f of x equals g of x plus c. Well, to do that, make a third function, call it h of x, which equals f of x minus g of x. And take the derivative of h. By the sum difference rule, that would be f prime of x minus g prime of x. But under the setup, f prime of x equals g prime of x, so this difference is 0. So we get h prime of x equals 0 on the interval from a to b. And our previous theorem says that if this derivative equals 0 on the interval from a to b, then this function h has to be constant. H of x equals a constant c by the previous theorem. Now remember, h of x was f of x minus g of x. So we get f of x minus g of x equals c. And switching that around, f of x equals g of x plus c, as stated here. So we've just proved it. If two functions are differentiable on an interval and their derivatives are equal, then one function equals the other plus a constant. This fact is something that we'll come back to in part 5 of the course, as I mentioned, so keep it in mind. This is one of the reasons that we introduced the mean value theorem today. It's an important theorem, but this particular consequence will be especially important to us. So to recap, we've got the mean value theorem. If f of x is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there's a number c in the interval for which this equation holds. And we've got this clear picture of it here. It should be so intuitively clear, and I hope I've convinced you that you've really understood this for a long time. We've just put it into a precise language in today's lecture. And we have this consequence that I just derived. If f and g have equal derivatives on an interval, then f of x is just g of x plus a constant, as illustrated here. That's the takeaway from today's lecture. Coming up next, we'll talk about differentials and approximations, another topic that will be useful, maybe not so much in Calc 1, but if you go on to Calc 2 and 3, you'll see a lot of it. So work some exercises, and I'll see you next time. Goodbye.